Hey class. All right, this is lecture 11. This is the last lecture before exam 1. So everything between lecture 1 and 11 will be free game on this first exam that we have. I'll also be releasing a exam review. So for the first exam, just kind of going over everything we've talked about so far and making it real clear what you need to know for the first exam. Okay, so be thinking about that. Hopefully you're watching this lecture a little early. The earlier you do, the more time you'll have to study for your first exam. Okay. All right, moving on to the PowerPoint here. Okay, so in this one we're going to be talking about covalent compounds. We talked about ionic compounds in the previous lecture and how ionic compounds are a movement of electrons from a metal to a non-metal, and that movement creates a positive and a negative charge, and when those two come together that creates an ionic bond. And here we're going to be talking about covalent bonds, which is a sharing of electrons. Okay, just as a quick review, go ahead and pause the lecture and try out this quiz. Okay, awesome. So let's look at what we got here. So we have nickel, right, which is Ni. Nickel, we can't accurately just predict the charge off the top of our heads, right? It's one of those metals that has a charge that can change. Okay, and then we have sulfite. Okay, so hopefully we've memorized these, polyatomic ions. So sulfate is SO4, 2-, right? So by losing one oxygen, we drop down to sulfite, which is SO3, 2-. Okay. And if we look at the ratios here, we have 1 nickel for every 1 molecule of sulfite, which means the charges are going to be equal on the nickel and the sulfite. That gives you a 1-to-1 ratio. Okay, so we should have nickel 2, so that would be C, right? Okay. Awesome. So we talked a little bit about this, but what holds this sulfur to this oxygen, right? There's covalent bonds within polyatomic ions. So this lecture, we're going to talk about how to draw covalent compounds, how to name them, and how to recognize them, okay? So covalent bonds are going to be between two nonmetals, right? We talked about how nonmetals have high ionization energies. So they don't want to give up electrons like metals do. So when you have, and hydrogen, just to point out real quick, hydrogen is on the left side of the periodic table, but it's considered a non-metal, okay? So when you have two nonmetals, right? So let's say you have a hydrogen and another hydrogen. Neither one of these hydrogens wants to give up an electron. So instead of giving one up to another, they basically just share it with each other, okay? This drawing, I think, is the best way to see that. They're sharing those two electrons between the two atoms of hydrogen. Okay. Okay, so we talked about octet rules, right? And how the different atoms want to see 8 electrons in their valence shell. They want to have 8 valence electrons, just like the noble gases, right? So Lewis dot structures are a good way to kind of visualize what covalent molecules look like, right? And using the octet rule, we can kind of predict what these molecules are going to look like as the atoms go together, right? Okay, so hydrogen has 1 valence electron. Okay, you see that here. And then fluorine has 7 valence electrons. Okay, so if we're going to do a covalent compound between these two, we're not going to transfer any electrons. We're simply going to take the single electron on fluorine and the single electron on hydrogen, and we're going to share them between the two, okay? And so the Lewis dot structure is going to look like this, okay? A line signifies a sharing of electrons. And then when you see two dots right next to each other, that's called a lone pair, okay? Lone pair. Okay, and that just means that those electrons are on fluorine. So now if we looked at the octet rule, okay, fluorine has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. This line counts as 2 electrons because it's sharing with hydrogen. So fluorine is satisfied by the octet rule. Hydrogen, if you remember, doesn't follow the octet rule. It just has 2 electrons, 2 valence electrons, because it's only in the first energy level. So it only has access to the s sublevel, which holds 1 orbital, which holds 2 electrons, okay? All right, moving on, let's look at another example. So let's look at oxygen. Okay, oxygen has 6 valence electrons. And if you remember, when we talked about the valence electrons, we said that you're going to put, if a molecule has, like oxygen has 6 valence electrons, you're going to start by putting electrons as far apart away as you can, and then you start putting them together if you have extra. So you'll see that as we move on down. But oxygen with 6 has 2 lone pairs, okay? One here, and then it has 2 free electrons, okay? Each hydrogen has 1 free electron, and instead of transferring, we're simply going to share electrons between the hydrogen and oxygen, and this oxygen and that hydrogen, right? The oxygen has 2 points where it can make a bond. Okay, and the Lewis structure would look like that. Okay, nitrogen has 5 electrons, right? So you can kind of see how many bonds nitrogen's going to have just by looking at how many valence electrons there is. So we have 1 lone pair here, and then we have 3 other electrons, each of them unpaired, which means we have 3 spots open for a bond. Okay, so nitrogen generally has 3 bonds to it. Okay, if we line up all the chlorines around here, we can see that each chlorine has 1 free spot for a bond. Okay, so again, just going to be sharing. They're all nonmetals. They're going to be sharing electrons, and so the Lewis dot structure would look like that. Okay, stitching these together like this is called the we call it the Lego approach to drawing Lewis structures. The book has a different approach, and I'm going to talk about both, and you can decide which one's best for you. Okay, so CH4, again, now carbon has 4 electrons, and we draw them all apart, right? So we can look on the periodic table and find out that carbon has 4 valence electrons. You might be tempted to draw that like this or something, right? But that means that carbon has 2 lone pairs and no free electrons. Remember, you draw them as far apart as you can, and then if you have extras, you'd go back and draw it. For example, nitrogen, right, has 5, so you draw 4 all apart from each other, and then that last one that you have, you'd put into a lone pair. But for carbon, there's only 4, so we're going to leave it like this. Hydrogen, each one has 1. You're going to do the sharing of all those electrons, and that's your Lewis structure with no lone pairs on any of these. All right, and then here's just C2H6. Again, lots of connections, and you get the Lewis structures here. Okay. Moving on. So kind of as a general rule, like I was talking about, you can look at the number of valence electrons. So if you're in group 14 or 4A, you're going to know that there's 4 valence electrons. And because there's 4 electrons, they're all apart from each other. These are like 4 different access points for a bond. There's usually 4 bonds there. Nitrogen has 1 lone pair, which takes up one of its access points, and it has 3 more spots where it can form bonds. Oxygen has 2, fluorine has 1, and then the noble gases of all lone pairs, they already have a full octet, so they don't have any bonds that they form with. Another one I'd add on here is hydrogen. So hydrogen's in the first group. Okay, it has 1 valence electron, and it forms 1 bond, right? Because it's got 1 free electron to share with someone else or with another atom. Okay, So there are some exceptions you'll see, but pretty much always these are the rules you're going to follow. All right, diatomic gases. So I think we talked about how like when fluorine or chlorine or bromine are on their own, they actually exist as a pair. And the reason for that, right, is because this is very unstable for a hydrogen just to have one electron and just be sitting around. So there's always another hydrogen close by, and so it's much more stable for them to share their 2 electrons than they have their valence shell filled with electrons. Same thing with fluorine, right? On its own, fluorine only has 7 electrons. It wants a full octet, so the answer is just to share with another fluorine close by, and you have fluorine gas. And that's true for all the halogens. Oxygen and nitrogen also exist as diatomic molecules, right? If you look at this here, oxygen has 6 valence electrons, and this oxygen has 6 valence electrons. So you can imagine sharing, right, like we've talked about, between these 2 electrons. But still at that point, oxygen doesn't have a full octet, right? So if I looked at just the oxygen on the left, we have 1, 2, 3, 4, 5, 6, because there's a bond, 7, so it still doesn't have a full octet. So in order to fix that, they do another sharing with their other available electron, and you actually have a double bond, okay? All right. Nitrogen, similar story, but it shares 3 times, and you get a triple bond. So you can have double bonds, you can have triple bonds, and those are the ones, you'll see doubles, you'll see singles, doubles, and triples, basically is what you're gonna see. Okay. All right. Okay. All right, let's go through an example. So let's say you're given a molecule like this, hydrogen cyanide. You're trying to figure out how to draw the Lewis structure for it, okay? When people start doing this, I think the most difficult thing is to know in which order to put the atoms, right? Like which one goes in the middle, right? Does nitrogen go in the middle, or does carbon go in the middle? And really there's only one way to draw it. So if you try it, I mean, you just start trying Lewis structures and you'll find out it's not going to work if you don't have it in the right order. For example, let's say you're drawing this. The order that it's written doesn't necessarily mean that's the order you're going to see it on a Lewis structure. So you might draw out nitrogen, right, and draw your electrons around it. Okay, and then you could draw hydrogen and then draw carbon over here. Okay, well, if you start connecting these, you can make a bond between hydrogen and nitrogen. You can make one here between nitrogen and carbon. You have another electron you could do here, but then you have these free electrons on carbon, so it doesn't really work, right? So let's try this out again. Put carbon in the middle, which just a little tip, carbon usually goes in the middle, okay? And we'll do nitrogen with its 5 electrons, and we'll do hydrogen, okay? And then you can see here, you connect this hydrogen to carbon, that works. This carbon to nitrogen, then you have another access point, another access point. And so if you rewrote this, you would see it looks like this. Okay, and that would be your Lewis structure for hydrogen cyanide. So it's really only one way that's gonna work on most of these. There are some where there are multiple Lewis structures possible. We'll talk about those at the end of the PowerPoint, or towards the end of the PowerPoint. Okay. Oh yeah, the books approach. So I just did the Lego approach that we talk about. The books approach says count up all the electrons first. Okay, so, and what I mean by that is the valence electrons. So hydrogen has 1 valence electron, carbon has 4 valence electrons, and nitrogen has 5 valence electrons. You add that up, you'd get 10 electrons, right? So 10 total valence. And then what you do is you start listing out your elements. So you put carbon, hydrogen, and nitrogen, and then you first draw single bonds between everything. but that only accounts for 4 electrons, because remember, every bond holds 2 electrons, right? It's a sharing of 2 electrons. So we have 1, 2, 3, 4, okay, and then we need to start adding in more electrons in order to complete the Lewis structure. So we could add some on carbon if we want. Hydrogen can't take any more, right? So let's say we start adding more. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, you can see there's an issue here, right? Because carbon has a full octet. It's got 8 electrons around it. Nitrogen only has 4. So what you do at this point is you say, okay, nitrogen needs more, so let's share these 2 with nitrogen and these 2 with nitrogen. If we rewrote that, we'd have hydrogen connected to carbon, connected to nitrogen. And you can count those up and see that carbon has a full octet, nitrogen has a full octet, and hydrogen has 1 bond, like it's supposed to have. Okay. Yeah, so I started drawing extra electrons around carbon. You could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then in that case, start sharing back with carbon. That's fine. Yeah, okay. Similar thing. You're going to get there in the end. Okay. And the Lego approach is what I just told you about, which is a pretty simple way to look at it, I think. All right. So we see the same pattern, right? Nitrogen has 3 bonds, carbon has 4 bonds, and hydrogen has 1 bond, like we talked about before. Okay, so we talked about how polyatomic ions have covalent bonds. So that means we should be able to use Lewis structures to draw them. So if we looked at hydroxide, for example, okay, if we're using the Lego approach, you have your oxygen here and your hydrogen here. Make a connection between the oxygen and hydrogen. And then you look back at the original, right? This looks weird because oxygen only has 7 valence electrons. 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, 6, 7, right? Hydrogen's good, but oxygen needs 1 more electron. Well, if you look, there's a charge here on the hydroxide ion, which means we need to be adding in another electron. Okay, so you can pop in 1 more electron on the oxygen, okay, and then you put the negative charge by the oxygen, signifying that that has an extra electron around it, okay. This negative charge that you see here is referred to as a formal charge, okay. And another way, before we go there, another way you can draw this, you'll see this in the book sometimes, for polyatomic ions, they'll draw the molecule and then they'll put brackets around it and put the charge outside of the brackets. That works too, whatever you want to do. All right, for phosphite, so let's go ahead and walk through it here, like the Lego approach. So you can create bonds between this oxygen and phosphorus, this oxygen and phosphorus, and this oxygen and phosphorus. All right, and I guess, sorry, before I go there, oxygen has 6 valence electrons, phosphorus has 5, right? So that's what we do first, and then we draw on the bonds, okay? So you can see you have this extra electrons on oxygen that are sitting around here. Okay, you need 1 more electron basically on each of these oxygens to fill the octet. And if you look here, you have a -3 charge, which means you can add 3 more electrons, or you need to add 3 more electrons into the Lewis structure. So you give each oxygen an extra electron, and that puts a negative charge on each of those oxygens. Okay. So oxygen generally forms 2 bonds. If it only forms 1 bond, then it has a negative charge on it, right? You could think about it like if oxygen normally forms 2 bonds, and then you instead of having 2 bonds, you have 1 bond. It's not sharing as many electrons, so it's keeping more electrons for itself. So since it has more electrons, it would have a negative charge on it. Okay. All right. Go ahead and try and draw the Lewis structure for ammonium. All right, coming on back here, let's walk through this problem, okay? So if we look at the LEGO approach, we have NH4, okay? So I guess this is moving a little bit fast on the LEGO approach. Let me take it a little slower here. Okay, so we got 4 hydrogens. All right, there we go. So now we connect all these free electrons, and then we would get to this structure here, right? And at this point, you might just want to like connect this electron with that electron, which is what we want to do, but then you have this other electron sticking out. If you did connect this hydrogen and this nitrogen, then nitrogen would actually have 9 valence electrons around it, and it can only have 8 valence electrons around it. So there's a plus charge here, right? So you actually need to remove 1 electron, right? And as you remove an electron, you gain a positive charge. So then, after you remove the electron, then you have the free electron there, which can form that bond with hydrogen, and that positive charge still sticks on the nitrogen, okay? The book's approach to doing this would be add up all the valence electrons, like before, right? So nitrogen gives you 5. Each hydrogen gives you 1 valence electron, times 4 would be 4. And since there's a positive charge, you remove 1 electron. So 5 plus 4 minus 1 would be 8 total valence electrons. And then you go ahead and draw your nitrogen, your hydrogens. Oh, sorry. Let me back up. Okay. Okay, we don't have the drawing here. Okay, so the book approach would be draw all your different atoms here. Nitrogen, hydrogen, hydrogen, and then draw single bonds between everything. And at that point, you can tell that you have 8 electrons already. 1, 2, 3, 4, 5, 6, 7, 8. 4 bonds times 2 electrons per bond gives you 8 electrons. So you don't need to draw any extra electrons. You're done at this point. You do need to, you could put the positive charge on the nitrogen. If you're not sure exactly where the positive charge is, just do the brackets and put the positive charge on the outside. You know it has to have a positive charge somewhere because there's a positive charge on this polyatomic ion. Okay. Cool. All right, carbonate. Walk through this one. So the book approach is going to have you add up all the valence electrons. You get 4 from carbon. You get 6 from each oxygen, and 6 times 3 is 18. And you have a negative 2 charge, so you need to add 2 electrons. So 4 plus 18 plus 2 is 24 valence electrons. So you draw out your carbon, you draw out your 3 oxygens, and draw single bonds to everything, okay? So 3 bonds that you have so far is a total of 6 electrons out of 24. So there's 18 more that you need to draw. So at this point, you start drawing lone pairs around the oxygens first, right? That's the easier way to do it. Start drawing lone pairs around the oxygens, okay? And 9 lone pairs gives you 18 electrons, okay? So if you draw lone pairs around each oxygen, 3 around each one so that they all have a full valence, then at this point you've added in all the electrons that you can add. You have 24 electrons on here. The only thing that's not done yet is that your carbon only has 6 electrons around it, right? So it needs 2 more. So this is where you would go ahead and donate 1 lone pair in so that you actually have carbon with 8 electrons around it, okay? All right, so there you go. And this is where we get into the idea of resonance, okay? Let's go through the LEGO approach real quick. Okay, LEGO approach, you draw each atom with the number of valence electrons it has. Then you start making connections, okay? You can connect these 2 electrons between the carbon and oxygen, and then a single bond between this carbon and that oxygen. It leaves you with 2 electrons that are unpaired here, but you have an overall negative 2 charge. So you add 1 electron in each oxygen, okay? And you get a negative charge on each oxygen there, okay? So you could draw it like this with a negative charge on the oxygen, or you could draw it with the bracket and the -2 on the outside and then don't put any charges in the middle, right? It's up to you. All right. So what you notice on this one is I took these electrons, if you're looking up here, from this oxygen, I put them down to form this right here. Well, I could have taken the electrons from this oxygen and pulled them down, and then I would have had something that looks more like this right here. Or I could have taken the electrons from this oxygen and put them down, and I would have something different, right? So there's 3 different Lewis structures that actually work for this molecule. So when you have a molecule that has multiple correct resonance, or sorry, multiple correct Lewis structures, it's said that the molecule has resonance, okay? And then all these structures are called resonance structures, okay? And that's what we're talking about here. So here there's a 3 different structures you could draw. You could just, if you remember from the previous slide what we had, you could have a double bond to that oxygen, to the oxygen in the bottom right, or the oxygen in the bottom left. These 3 structures are called resonance structures. Okay, carbonate, you would say, has resonance. Okay, those are kind of the terms, just walking through those. Chem 285 this is going to be a big topic. We'll talk about resonance a lot, but for this class, what's important here to know is if I give you the only molecules that you'll probably see that have resonance are some of the polyatomic ions. Okay, so if you're asked to draw the resonance structures for carbonate or sulfate or something, you'll just need to be able to draw out all the different resonance structures for those. Okay. All right. Or if a question says, does this molecule have resonance? Then you would draw out the Lewis structures, and if you see that there's more than one correct Lewis structure, then that molecule has resonance. Okay. All right. Technically, this structure on the far right is a resonance structure as well. It's kind of a weird one. I wouldn't really ask you to draw that one on an exam. Just these 3. Okay. All right. The idea of resonance, it's kind of shown here, and this is just kind of a concept, is that these negative charges, if you just draw this version, you're saying that the negative charge is on this oxygen, and that this oxygen doesn't have a negative charge on it. All right, remember, if oxygen has 1 bond, it has a negative charge. If it has 2 bonds, it has no negative charge. Okay, but the real picture is that these negative charges are shared between all of these oxygens. Okay, and that's kind of what's shown here. You have these symbols mean partial negative. So you have these negative charges shared around all the oxygens. Okay. Pause real quick and try this quiz. Okay, sodium oxide, right? So this is good review. The sodium with a plus charge on it. Oxygen has a -2 charge. So we need 2 sodiums for every oxygen. All right, so we should choose B. Okay. All right, so now we're going to talk about naming covalent compounds. We talked about naming ionic compounds. And with ionic, there's the way to name it when you know the charges, and then if you don't know the charge of the metal, then you use the Roman numerals. Covalent compounds are easier to name. You first just put the first nonmetal by its name, okay? Then you put the second nonmetal with the IDE ending, okay? IDE before was associated with a negative anion. In covalent naming, it's not really associated with the negative anion, it's just the second name gets the IDE ending. And then you use prefixes to say how many atoms you have of each nonmetal, okay? So these are the prefixes, right? Mono, di, tri. Usually those are the only ones you're really gonna see. You might see tetra, maybe hexa. Anyway, they're pretty these are pretty common prefixes, so hopefully you know these already. Okay, so let's look at some examples. So when you see a formula, right, for a covalent compound, and you know it's covalent if it's two nonmetals, you just say the name of the first atom, so that's a carbon, and sulfur would be changed to sulfide, right? And because there's two sulfurs, it would be disulfide. So carbon disulfide, right? You've probably seen or heard about this one. So you have a carbon and an oxygen. So carbon gets its full name. Oxygen is switched to oxide. And there's two oxides, so it's dioxide. So that's carbon dioxide, right? NO would be just nitrogen oxide. You could say nitrogen monoxide if you wanted to. But if it's omitted, if you don't see a prefix, then you just assume it's one. So nitrogen oxide, there's no prefixes on nitrogen, no prefixes on oxide. So we're going to assume there's one nitrogen and one oxygen. Here we have a dinitrogen oxide, so I'm going to assume there's two nitrogens. There's no prefix on oxide, so there's going to be one oxygen. That's where you see here, two nitrogens, one oxygen, okay? Same thing here, silicon dioxide, sulfur dioxide, sulfur hexafluoride, right? There's one of your hexa ones. So the naming for covalent compounds is hopefully pretty straightforward there. All right, let's go and practice this real quick. So write the correct name, correct formula for each of the following. Phosphorus, the element symbol is a P. And we only have one phosphorus because there's no prefix on it. So I'm not going to put a number, right? You don't put a number if there's only one. Pentachloride. Okay, so that's a chloride. And there's 5 chlorides because you have a penta. So that would be your covalent compound right there, the formula. Dinitrogen, so we have 2 nitrogens. Trioxide, 3 oxygens. Sulfur, there's no prefix, so we're just going to do 1. Hexafluoride, so we'll have 6 fluorines, okay? Okay, sweet. All right, that's it for the covalent presentation. Kind of a lot of information in that one too, but I think resonance, drawing Lewis dot structures, practice that. Just practice knowing if there's resonance in a certain molecule and how to draw resonance structures for the polyatomic ions, and then how to name covalent compounds. Those are the 3 big ideas from that presentation, and there should be some practice in your homework for that. So, all right, I think that'll be it for this lecture. Make sure to let me know if you have any questions as we head into the exam, and watch out for the exam review because it will go over what's going to be on the exam and what you should know and everything like that clarified. So, all right. Have a great weekend. Well, I'm recording this on Friday. You're probably going to maybe watch a different day, but have a good weekend.